So far, we have covered the pipes model and the general stimulus response and the GHR and GM models. The next car following model that I would like to cover in the second part of the lecture today is PIT model. Based on the assumption that the follower vehicle attempts to maintain a fixed time headway between its front bumper and the rear bumper of the lead vehicle, the PIT model assumes that the distance between these two vehicles is actually proportional to the speed of the follower and the speed difference between the leader and follower. So again, if you look at the equation here, S here is representing the spacing between the leader and follower. So if this is the follower and this is the leader, spacing is from the front bumper to the rear bumper. So if this is the front bumper of the follower and this is the rear bumper of the follower, here it's called Sn+1t. Okay? So the distance between the two vehicles, or in other words, a spacing between the two vehicles, can be calculated as, let's first have a look at this, the last term, which has the difference between the speed of the follower and the speed of the leader. So the difference between the speed of the two vehicles, power 2, interesting, multiplied by B and K, which are sensitivity parameters, which again has to be calibrated or assumed, plus the speed of the vehicle multiplied by that K, the same sensitivity parameter, plus the length of the vehicle, plus the buffer distance between vehicles at a standstill. I mean, this is similar to the small bi we had before, but because I'm using this B again here, I'm not going to use the same B as before. So it's shown as the capital B here, but it's the same as the small b that we had in the stimulus response and in the pipes model, if you remember. So this capital BN is the safety distance between vehicles at a standstill. Ln is the length of the vehicle. B, small b, and K are sensitivity parameters. And the spacing in the PIT model, as we just talked about, is mainly a function of the speed differences, power 2, and the speed of the follower. Interestingly, the difference between the PIT model and if I go back to the GHR model is, look, in the GHR model, we have the difference between the speeds, but there's no power. It's power 1, right? So whatever the speed difference is, it affects the acceleration. But in the PIT model, it's power 2. That means it's very sensitive. By adding this power to the difference between the speeds, we make calculation of the spacing a little bit more sensitive to the difference between the speeds. So if the difference between the speeds increases, the spacing actually increases with the power 2, not necessarily in the same range. So that's how spacing works in the PIT model. And now, again, we can represent the spacing as I said, xn minus xn+1, right? And if we try to replace this, S in this equation with xn minus xn+1, and if we assume constant acceleration, let's do some mathematical derivations to actually get the speed and acceleration equation from the PIT model, okay? So we say the spacing is actually equal to the difference between the location of the follower and leader at time t plus delta t. If you replace this xn+1 at t plus delta t with constant acceleration formula, if you remember from a previous lecture, we derived the formula for constant acceleration, right? Which is coming from basic kinematic physics. And if you replace this with the constant acceleration formula, we'll get xn+1 at time t is equal to the speed multiplied delta t plus 1/2 acceleration delta t power 2. If you remember from physics, it's a very common formula to use in kinematics. And if we can also express this v here as a function of acceleration, right? So speed at time t plus delta t is actually the initial speed at time t plus acceleration multiplied by delta t, right? This is again this is v t is equal to v t0 plus a t, right? Plus a t. This is the simple speed and acceleration relationship from basic physics, from basics of physics. So if I also replace this v with this acceleration function, and then if I keep the acceleration on one side and move everything else to the other side, I can actually derive a very long formula for the acceleration of the Pitt model. Again, don't worry about how it looks like, but I just want you to show you how is this different compared to the acceleration function of the previous models that we talked about. So in this case, you can see that what is interesting in the Pitt model is that acceleration at time t plus delta t follower is actually dependent on the difference between the speed of the follower and vehicle, but at two different time intervals. Look, previously we had vnt minus vn plus 1t. So, sorry, it was all t or t plus delta t. So in previous car following models, we were always looking at the difference between the speed of the follower and leader at the same time. But in the Pitt model, when we want to calculate the acceleration of the follower at time t plus delta t, what comes here in the formula is the speed of the leader at time t plus delta t minus the speed of the follower at time t. So the difference between the speed of the follower and leader at two different time intervals come into play. And it has the power 2, obviously. We also have the speed of the follower at time t. We have this safety distance. We have this ln. We have the difference between the location of the vehicles or spacing, right? And again, same thing happens here. We are looking at the difference between the location of the leader at time t plus delta t minus the location of the follower at time t. So the spacing is also being calculated at two different time intervals. And then we have this k, which is the same parameter in the model, and the rest is delta t. So I just wanted to highlight this difference between the Pitt model and all the previous models that we talked about, that the Pitt model actually looks at the two different time intervals, compares the difference between the locations and the difference between the speeds from t and t plus delta t. So parameter b is a constant, which usually takes the value of 0.1 in the Pitt model. When the speed of the follower is larger than the speed of the lead, it takes the value of 0.1, and if the speed of the follower is equal to the speed of the leader or smaller, b becomes 0. What this does is, what this rule here, what this assumption or what this input does is, when the lead vehicle is traveling faster than the follower, their speed difference does not matter, and it does not affect the acceleration of the following vehicle. The speed difference only matters, and it only affects the acceleration when the follower moves with the same or a smaller, with the same or greater, sorry, not the same. When Vn plus 1 is greater than Vn. So the speed difference only affects the acceleration when the lead vehicle is traveling faster than the follower. if the lead vehicle is traveling faster than the follower, the speed difference doesn't really matter. It only, so look, if this b is equal to 0, that means this term will go out regardless of what the time difference is. If b is greater than 0, in this case, if we assume b is 0.1, the speed difference comes into play because we have this constant b. We have this constant b in the formula. So that's how the PIT model works. If you want to, I think I touched on some of these differences between the PIT model and the GHR model. So unlike the GM model, the PIT model considers the final speed of the lead vehicle at end of the delta t. As I said, t plus delta t, right? I talked about this. The acceleration during delta t is estimated as a function of where the vehicle will be at t plus delta t. The perception reaction time of the driver need to be considered separately and after the acceleration is calculated. And the PIT car following model does not replicate traffic oscillations very well. So one of the shortcomings of the PIT model when we simulate traffic with the PIT model is that it doesn't replicate traffic oscillation. What does traffic oscillation means? We usually call that the stop and go as well, stop and go waves. So that's when speed goes high and then it goes down and vehicles keep moving and then keep stopping. That's called traffic oscillation. When we use PIT model in traffic simulation, unfortunately, it doesn't replicate traffic oscillations very well. And any traffic disturbance, any shock wave really diminishes very quickly. That's one of its shortcomings. There are many other car following models in the literature. There is one called Gibbs model. Gibbs model is a car following model that is implemented in AIMSUN, and originally it was developed in Australia. If that makes us feel happy. There's another model called MidSim. That's kind of an updated version of the GHR model, and there's also another model called Widman that is used in Vissim. Vissim is another commercial microsimulation software. So Widman is also widely used, and it's implemented in Vissim, as I said. So I have another optional task for you. I will give a bonus mark to any student who conduct a literature review on car following models. So what I would like you to do is, if you want to get that bonus mark, it's 1%. Conduct a literature review on car following models, including a comparative analysis on the advantages and disadvantages and calibration and validation requirements of different car following models. So a 5-page literature review on car following models. And if you do that in a week or two, and if you send me your literature review, I'll give you that bonus mark of 1%. So the next topic is lane changing. Lane changing is usually more complex than car following. Car following is mainly is based on physics, right? But lane changing involves human decision making, and that makes it very difficult to model sometimes. A lane change maneuver is likely to be affected by its urgency, whether it is imperative to change lanes to get position to turn or take your off ramp or take an on ramp, or sometimes it may not be as pressing to pass a slightly slower vehicle. Sometimes you have to change lane, sometimes you don't really have to change lane. So it's really affected by the urgency of the lane change itself. Drivers may change lanes with or without cooperation from the vehicles in the target lane. Sometimes you're lucky, the car that you're going to drive in front of it, it's a cooperative driver, and your life is easy. But if the cars that you have to get in that lane are not very cooperative, you're gonna find it very difficult to change lane, right? Interestingly, when it comes to lane changing, unlike car following that we had a lot of analytical relationships, there are no analytical relationships that encompass the entire lane changing process. So when it comes to modeling lane changing and lane changing process, there are multiple steps. The first step is the decision to make to change lane, is it a mandatory change lane or is it a discretionary lane change? A mandatory change lane is like when you want to turn or if you want to take an exit on a freeway, while a discretionary lane change is, for example, if you want to go a little bit faster, if you want to take over another vehicle, which you don't have to, but for example, if you want to go with a higher speed and you want to change lane, then you need to choose which lane you want to enter. You want to go from lane 1 to lane 2 or from lane 1 to lane 3, how many lanes you want to cross. Then the next step is gap acceptance. Is there sufficient gap in traffic for you to do to make the lane changing? And at the end is acceleration and deceleration to actually change lane, because usually when it comes to lane changing, either you have to speed up a little bit to make the lane change happen, or you need to decelerate a little bit and slow down to let the other vehicle pass, and then you change lane. So there is this acceleration and deceleration decision as well at the end of the lane changing process. So when it comes to lane choice, the decision whether it's mandatory or discretionary is it's a very intuitive decision. But when it comes to lane choice, which lane you want to change to, we usually use discrete choice modeling. So discrete choice modeling is a kind of modeling framework that allows us to model discrete choices. For example, I usually make this example that imagine you have vanilla ice cream and chocolate ice cream. Which one do you choose? You choose vanilla, someone else may choose chocolate. But how can we actually model this? It's not 1, 2, 3, 4, 5, 6 that we can model. It's not a numerical process. It's really a choice. How can we model choice? And that's where discrete choice modeling comes into play. That we say that if I have two options, if I have option 1 or alternative 1, let me call it alternative 1. If I have alternative 1 and if I have alternative 2, that could be vanilla ice cream versus chocolate ice cream, or it could be lane 1 versus lane 2. We define something called a utility function, and then we calculate that utility function for each alternative. For example, in case of vanilla ice cream and chocolate ice cream, the utility could be I don't know how sweet is the ice cream is, or whether you had a chocolate ice cream before or not. So whatever, just like a regression model, we can define a function that calculates the utility of that alternative. And then we also introduce an error term, which again, discrete choice modeling is a whole course by itself. So it's really hard to summarize it into a few slides today, but I try my best. And then we introduce an error term because there is this probabilities, right? We can't necessarily, in a deterministic way, predict whether you're going to choose alternative 1 versus alternative 2. But what we can do is more in a probabilistic way, that we can say with the probability of, for example, 0.8, you're going to choose alternative 1 versus alternative 2. So that error comes in to make it more of a probabilistic. So U is called a deterministic utility function, V is a probabilistic utility function. And then if the probability of alternative 1 is higher than alternative 2, we say you're more likely to choose alternative 1 because the probability of alternative 1 is higher. In terms of lane choice, what we do is we calculate the utility of each lane. For example, we calculate the utility of lane 1, utility of lane 2, and lane 3. In this case, if we have 3 lanes, and then we use something called a logit model to calculate the probabilities. The way the probability is calculated in a logit model is very simple. We say, imagine I have 2 alternatives, okay? Imagine I have alternative 1 and alternative 2. For each of them, I have calculated utility 1 and utility 2. And then what is the probability of alternative 1 being selected? Is the exponential of utility 1 divided by exponential of utility 1 plus exponential of utility 2. So this gives me the probability of alternative 1 being selected. And probability of alternative 2 being selected is exponential of utility of alternative 2 divided by summation of the exponentials of all the alternatives. So it would be exponential of utility 1 plus exponential of utility 2. So if you calculate these two probabilities, and if P1 is greater than P2, you can say you are more likely to choose alternative 1 over alternative 2. If P2 is greater than P1, you say you're more likely to choose alternative 2 compared to alternative 1. If P1 is equal to P2, that means it's just 50-50. You can either choose alternative 1 or alternative 2. So for example, in this case, if I want to make an example, imagine I have two lanes. I have lane 1 and I have lane 2. Imagine the utility of lane 1 is equal to, I don't know, 5, and utility of lane 2 is equal to 3. And if you want to calculate what is the probability of choosing lane 1, you just need to calculate this probability that says probability of choosing lane 1 is equal to exponential of utility of 1, which is 5, over exponential of 5 plus exponential of 3, for example. If you calculate this, whatever number you get, it's going to be between 0 and 1, definitely. And it gives you the probability of alternative 1, lane 1 being selected. I think the challenge here is what the utility function looks like lane choice. It could be a function of the driver characteristics, like its age, number of years of experience of driving, how congested the road is, the description of the characteristics of the car that I'm driving, the characteristics of the lane, whether the lane is congested or not, the composition of traffic. There's so many things that can be used to specify that utility function, which is beyond a little bit of what I'm going to cover today. But just wanted to let you know that coming up with a specification of this utility function is itself a big question. That how can we come up with this? As I talked here in this slide, that utility function can be a function of various factors such as road characteristics, the environment characteristics, driver characteristics, etc. In terms of gap acceptance, let me cover that also very quickly. So when it comes to accepting a gap, drivers usually evaluate the size of the possible gaps in the target lane. A driver may accept a gap or reject it and try to attempt to find an acceptable or reevaluate whether I can really make a lane change. There are many studies in the literature that are focused on lane changing behavior on freeways because that's easy to monitor and observe. But there are very few studies on lane changing behavior in urban arterials because that's very complicated. There are pedestrians crossing. There's so many factors involved when it comes to lane changing in urban arterials. Freeways is usually easier to study. Gibbs, the Gibbs car following model. Gibbs was actually developed one of the first lane changing models in the literature. If you search Gibbs lane changing model, you'll find some papers online that you can read if you like. But how do we actually model gap acceptance? Gap acceptance modeling seeks to predict whether a particular gap size should be accepted or should be rejected by the driver. To do that, we define something called critical gap, which is defined as the minimum gap that a driver is willing to accept. The size of the critical gap varies significantly depending on the type of the maneuver. Is it lane changing on a freeway segment, or is it making a left turn at a stop controlled approach? Is it a yield sign? And also the driver characteristics. Am I a young driver? Am I an old driver? So the size of that critical gap varies between you and me. But the challenge in modeling that gap acceptance behavior is observing the gaps that drivers reject, because the critical gap cannot be directly measured. It is usually inferred based on the gaps drivers accept and not those reject, because I can only see when you make a change lane and when you accept a gap. When you do not change lane, when you basically reject the gap, I can't really see it. I don't know what's happening in your mind. Are you really looking to change lane and you just rejected this gap, or you just not want to make a lane change? So observing the rejected gaps is really hard in reality, but what we usually see in reality when we collect data on traffic is we only see the accepted gaps. So one of the most popular methods for critical gap estimation is actually called maximum likelihood estimation. The way it works is using the maximum rejected gap and the accepted gap for each driver, we estimate the critical gap between the two values. So imagine we have the cumulative distribution of accepted gaps. Let's call that FA for each driver. We also have the cumulative distribution of the maximum rejected gap. Let's call that FRJ. And then the probability that the driver's critical gap, the critical gap can be represented at TC. So the probability that the probability that a driver's critical gap is between, for example, Ri and Ai is actually equal to the difference between the cumulative distribution of the accepted gaps minus the cumulative distribution of the rejected gaps. So to better understand it, don't worry if it's a little bit too hard to follow. I want to show it to you graphically how it looks like. So imagine I observe one single driver many times. He or she is making lots of lane changes or crossing traffic, and I observe many of the accepted gaps and the maximum rejected gaps that I see. So the blue curve is the histogram of the accepted gaps, and the red curve is the histogram of the maximum rejected gaps. If I convert these histograms, so these are histograms or the frequency plots, if I convert them to a cumulative distribution plot, hopefully you know this from statistics. Here I have the cumulative distribution of the accepted gaps, FA here, and I have also the cumulative distribution of the maximum rejected gaps, FR here. And the probability of the critical gap being, so for example, look, if I say what is the probability of the critical gap being 4.5 and 7, the critical gap being between, the critical gap was TC, being between 4.5 and 6. This is the horizontal difference. Sorry, this is the horizontal difference, the horizontal distance. The probability of the critical gap being between 4.5 and 6 is actually equal to 0.6. You see that in the graph? So that's how we probabilistically try to understand what is the critical gap of any individual driver. And now imagine I have a sample of n drivers, and I want to calculate what is the critical density, critical gap for all these drivers. The way it works is we calculate something called likelihood function, which is multiplying all the probabilities for each driver. We multiply the probability of TC of driver 1 multiplied by driver 2, driver 3, all the way to the end. And then if you take the logarithm of this likelihood function, this multiplication becomes a summation, if you remember from logarithmic operations in math. And then if you try to maximize, if I want to maximize this likelihood function, log likelihood function, what do I do? This is called log likelihood function. Just need to take the derivative of this and make it equal to 0, right? So we take the derivative with respect to the mean of the distribution of the critical gap, and we also take the derivation of the log likelihood with respect to the standard deviation of variance of the critical gap distribution. If I make it equal to 0, I come up with the critical gap. I can estimate the parameters of the critical gap by taking the derivative of this log likelihood function with respect to mu and the variance. So some of the limitations when it comes to gap acceptance is that most of the gap acceptance models assume drivers are very consistent and homogeneous, where in reality drivers behave very differently. Of course, these assumptions are not realistic, and they have actually proven to be acceptable. But they have, although this is not a realistic assumption, assuming that drivers are very homogeneous and consistent. But again, there are many studies that have looked at it with real data, and they said it's okay in terms of modeling accuracy to assume drivers are consistent and homogeneous. But again, there are also some studies that have taken into account driver heterogeneity and driver inconsistency to calculate to estimate the critical gap.